Hi, we are Iztech Cengaver Rover. Our team was established in 2022 in Izmir Institute of Technology. In the first year of our team, there were only 10 members. As the team continued to grow from there, we now have 25 members from 3 different faculties and 10 different departments. The first competition the team was participated in was ARC'23, and in this year we are hoping to be in a part of ARC'24 too.
The team is divided into 5 different sub-teams: mechanical, electronics, coding, science and social. Sub-teams work as a unit to create rover that is developed to overcome different types of challenges.
Cengaver 2 features a dependent 4-wheel rocker suspension system with rockers interconnected by 4 rod and bearings. Each rocker is designed to withstand loads up to 300 kg from the robotic manipulator position. A specialized unloading method has been used during the rocker's design phase to mitigate bending moments and manage the inertia effectively. To produce lightweight and durable rover, we produced our material from aluminium 6061, 6070 and 6080. Weight of the rover is approximately 50 kg with robotic manipulator and drilling mechanisms. Rover size is 85 cm in x-axis and 95 cm in y-axis and 42 cm in z-axis. This design allows the rover to navigate extreme terrain, including obstacles up to 1.5 times the diameter of its wheels, thanks to its low center of mass allowing us to steep angles up to 45 degrees. The driving module incorporates all-wheel drive functionality utilizing DC motors with planetary gear systems to facilitate traversal of slopes within the ARC competition zone. Traction is enhanced through the use of customized tire manufactured from TPU95A material. Furthermore, the hub drive system integrating 2 slim bearings not only enhances the assembly rigidity but also optimizes power transmission efficiency.
Manipulators weighs 15 kilograms and can reach up to 110 centimeters when fully extended, and has 5 degrees of freedom. Everything is aluminum except shafts. Shafts are chrome strengthened steel. Due to that, our manipulator is light and also strong. For high precision, we use 3.5 mm stepper motors with 50-to-1 planetary gearbox to actuate the links, and DC motors to actuate the grippers. To decrease the torque requirement of the system, we use the parallelogram mechanism and carried one of the actuators to base and used 3 bevel gears to create a swing mechanism. We are actuating both links at the same axis with 2 shafts are concentric and supported with bearings between. With this system, we decrease the load on the links and torque requirement of the first actuator. Also, for the minimalized friction, ball bearings and thrust bearings are used. Increase the use of manipulator, we are planning on using hybrid control system where we control the 5-pipe parallelogram mechanism with inverse kinematics and other axes with forward kinematics.
For the rover's manual, autonomous and the manipulator systems control, 3 different coding fields are necessary: embedded system control, control interface, and navigation for autonomous drive. This field requires Python, C++, Vue.js programming languages, and XML. As the main computer of the rover, NVIDIA Jetson Nano, which is operating by Ubuntu 18.4, used it as the main controller. Raspberry Pi Pico is operating on the rover. The main communication system between software devices and embedded system is established by ROS2. To implement ROS2 and Ubuntu 18.4 properly, ROS2 is used as a Docker container.
For the development of the web interface software running on Cengaver 2, WebRTC protocol to connect the rover to Vue.js frontend of the rover was used. The main purposes of the web interface is for the rover to be controlled manually and its systems to be controlled via the web. The WebRTC protocol is used to connect the rover's cameras to the Vue.js frontend. The control of the software running on Jetson Nano with the Docker images and the surveillance systems on the rover were developed by the team's great endeavor.
Embedded part of the coding is responsible for programming the hardware that the rover relies on to do anything. Raspberry Pi Pico is chosen to be used as microcontroller as it's a dual-core microcontroller that is very fast and has great integration with frameworks such as MicroROS and FreeRTOS. The main responsibilities of the microcontrollers are controlling the DC motors, controlling the robotic arm, and reading the data of all sensors. To ensure the motors are always at the exact speed needed, quadrature encoders on DC motors and a use of a PID algorithm was required. In addition, controlling the robotic arm is provided by inverse kinematics. At the end, Data sensors such as absolute orientation of the robot, soil analysis, and temperature are gathered.
To provide autonomous drive, a GNSS model is used to determine rover location. Computer vision scripts were developed to make pose estimation with respect to ARC'. SLAM algorithms are used for mapping and making localization according to the environment. To make SLAM algorithms properly, a simulation of the rover in a URDF file, which represents the rover physical properties, such as mass and inertia, in an XML file was made to predict the rover's physical behaviors for collision calculations. This simulation of rover was created from an extension in SolidWorks and was set at the joints manually in the XML file.
A 29 amp-hour lithium-ion battery configured in a 7 series and 10 parallel setup powers the rover. The battery's power is regulated by a distribution board to provide 24 volts, 12 volts and 5 volt outputs. While maintaining communication, an emergency stop button on the rover disables the manipulator and mobility system in unusual situations. To operate in dark environments, a modular 100-watt power LED has been integrated into the front of the rover. The battery pack, weighing approximately 3 kilograms, is the main component of the electronic system meeting the rover's power needs.
A custom PCB was designed to establish connections and install necessary circuits within the rover. During this design phase, particular attention was given to adhering important design rules for the motherboard. After production was completed, signal integrity testing was conducted and PCB have been tested separately with target rover parts to ensure proper functionality.
Local Wi-Fi networks were set up on the base station and the rover for secure communication. Remote control of the rover was enabled using a Tenda V6 access point, which is allowing communication up to 2 kilometers with the antennas. A 3 kilograms, 2.5 meter antenna is deployed at the base station.
As Iztech Cengaver Rover science team, we recognize that geological units not only document the deposition of relatively recent ejecta from impact craters, but also indicate the presence of units from earlier periods.
By employing specialized tools, our onboard camera will identify and characterize the unique geological features and mineral compositions present in the region. Our science sampling system has 3 main components: drilling into the ground using 2 DC motors with a screw mechanism, attaching a scoop to gather soil, and securing samples in a specialized box. The box has 5 sections. 4 for soil collection and 1 for containment. Each section contains 4 tubes for chemical tests. The box's cover is initially closed and compressed with a mechanism, then upon extraction it rotates by 72 degrees using a DC motor and rotary encoder. Samples are transferred using a high-precision robotic manipulator, and after sampling, the box closes again with the cover compressed.
Our scientific mission involves 2 primary objectives. Firstly, we employ specific regions to thoroughly examine soil samples for the detection of lipids and proteins. Moreover, we evaluate phosphate concentrations as a potential marker for microbial life using the molybdenum blue method. Secondly, we aim to assess soil's ability to sustain life by evaluating key ions and soil metrics such as pH, moisture content, and nutrient availability. A variety of sensors featuring the MQ series and atmospheric sensors are utilized. These sensors enable us to detect gases such as ammonia, carbon monoxide, methane, and carbon dioxide, analyze soil composition, and monitor atmospheric conditions and potential habitability.
Furthermore, we employ a custom-built visible spectrum spectrometer. Our spectrometer is designed to provide high-resolution data that is essential for the analysis of geological rock samples and comprises 4 key components: a light source, sample cuvette, light grading mirror, and detector. The detector measures the intensity of transmitted light, and based on our standard sample graph, the concentrations of iron and magnesium will be determined.
See you there!